Today we look at some of the most basic and useful properties of integrals. These are the properties we use all the time to evaluate integrals and to understand what they mean. These properties should be easy to remember, either from a geometric understanding of integrals in terms of area, or straight from the definition, which I'm showing you here to remind you. So, by the way, every time I say integral, I'm talking about Riemann integral or definite integral, same thing. The integral is the limit of a Riemann sum, which is a sum of terms that look like this. You take f evaluated at several points spread out throughout the interval, multiplied by delta x. From this definition, it should be obvious if you take your function and multiply by a constant c, that constant pulls outside the integral. That's because if you look at the Riemann sum, if you multiply the function f by a constant c, that's a common factor for all the terms in the sum. That constant factor pulls out of the sum, and then the constant also pulls outside of the limit because of the rules for limits, and that means the constant c pulls all the way out of the integral. And a very similar reasoning tells you that if you integrate f plus g, that is the integral of f plus the integral of g. That's because if you look at the Riemann sum for f plus g, you rearrange the terms and you get a Riemann sum of f plus the Riemann sum of g. And now the limit, this sum, is the sum of the limits, so you get integral of f plus the integral of g. But that's no surprise, since you're expecting this from knowing the limit of a sum as the sum of limits. The derivative of f plus g is derivative of f plus derivative of g. You expect the same thing to be true for integrals, and it is. But should be warned, the integral of f times g is definitely not the integral of f times the integral of g. But you wouldn't expect that, would you? Because you know that the derivative of f times g is not the derivative of f times the derivative of g. If you reverse the limits of integration, that's what we call a and b, the limits of integration. If you reverse them, that pulls a negative out of the integral. And the reason is, if you look at the delta x in the Riemann sum, the numerator is b minus a. Well, if you reverse the a and b, that gives you the negative of your delta x. So the negative pulls outside of the sum, which pulls outside of the limit, and so that makes the whole integral a negative of what it was. So to paraphrase, integrating backwards from right to left instead of in the natural order from left to right, that will give you the opposite sign for the integral from what it was before. Now, there's another way to get a negative coming out, which is, of course, if you replace f by minus f, because that's just multiplying by a constant minus 1. And from the previous slide, we know if you multiply the function by a negative 1, that negative 1 pulls outside. Just saying, if you turn the graph upside down, the integral becomes negative. So from these two facts, what you could say is if you reverse either the x or the y, then that makes the whole integral negative of what it was. And you can't really say that about area. You can't talk about area being negative. It's not what we mean by area. Area could be 0, but otherwise it's positive. Integrals can be positive, negative, or 0. On the other hand, if you take a positive function f, then the integral will be positive, at least if you're integrating from left to right, a is less than b. And this is because if you look at the Riemann sum, all the terms are positive, so the Riemann sum is positive, the limit of positive is positive. And there's a closely related fact, which is if f is less than g, then the integral of f is less than the integral of g. And, well, there's less area under the curve. But the real reason why it's true is if f is less than g, then g minus f is a positive function, and then you just use the previous fact that I mentioned. Now suppose we take the integral of f from a to b, add the integral from b to c of the same function. This should be the total integral from a to c. And the picture probably convinces you, but my picture is a little special. I'm showing you a picture of a positive function, which means that the area is just the integral. And if you take the area of the entire region, and I split up the region, you add up the areas of the parts, you should get the area of the whole region. There's another thing that's special in my picture, is that a is less than b is less than c. So my points are left to right on the x-axis, but that also doesn't have to be the case. You can change the order of the points. You can change the function being positive. It can be positive, negative, or sum of each. And this rule will always work. So working with integrals, you don't have to worry really about things being positive or negative or what order. That takes care of itself. And now if you take a general function, it's going to be different from the positive function that I first considered to motivate the definition of integral. If a function is positive, the integral is area. But a typical function like this one is positive from a to b, it's negative from b to c, and it's positive from c to d. And when you look at the area between the curve and the x-axis, you get some of it is above, some of it is below the x-axis. Well, it's still true that the integral from a to d is the sum of these three separate integrals. But they're not all positive, so the first one is positive. It's the area that I called region A. And the second integral, in the middle, is negative. It's minus the area of B. And the third integral is the area C, which is again positive. So, in other words, if you integrate, what you're getting is the total area above the x-axis minus the total area below the x-axis. In this example, by the way, it looks like the total integral will be positive. There's more area above the x-axis than below the x-axis. In fact, it pretty much looks like the areas A and B probably just about cancel each other out. If we integrate a constant, the answer is easy. The graph in this case I've shown you for a positive constant c, and I'm integrating left to right in my picture. I just get the integral as the area of this rectangle, length times width, so it's b minus a times c. Now this formula works for all constants a, b, and c. Positive, negative, whatever order they are in, this formula is always true. For area, you have to be careful because the area cannot be negative. This formula can give you a negative value for the integral. And by the way, the area is not always just simply the absolute value of the integral. Well, here it is, but on the previous slide it wasn't. If you look back at the previous slide, in the picture I showed you, the absolute value of the integral is not the total area. If you integrate from a to a, you just get 0. Think of it geometrically as the area under the curve, but it's a very thin area. The width is 0. From a to a, there's no width. The width is 0. If you try to approximate it using rectangles, it's a rectangle of width 0. Now, if you integrate from a to b, add the integral from b to a of the same function, you're going to get the integral from a to a. Here I'm using a previous rule where I went from a to b to c, but I'm using a special case of that, which is if c happens to equal a, it could, then the integral from a to b plus the integral from b to a must be 0. And then you can solve and get the integral from b to a is minus the integral from a to b. Now this is a fact that I mentioned before, and here I'm giving a slightly different explanation. Here is an example of a positive function. So the integral from -9 to 5 is just the area under the curve. But this is an example that you can work out using basic formulas for area from high school geometry. Namely, you look at the area under the curve and you decompose it into pieces that are simple geometric shapes of which you know the area. So the first piece is triangular. The area of that is half times base times height. That's half of 6 times 3. For the rectangle, the area is length times width, 8 times 3. Now, a circle has area pi r squared with radius 3 in this case. We have half a circle, so that area is 9 pi over 2. And you just add them up. You get 33 plus 9 pi over 2. That's about 47.14. And I should point out here that we used formulas from high school geometry. Those formulas are certainly correct, but most people don't appreciate why they're true. And in particular, the area of a circle is pi r squared. The only reason we have such a formula is because of calculus. You need calculus to see that. And it's probably more calculus than high school students know. They know this formula for the area of a circle. Anyway, when you're doing problems like this in the book, you're going to be breaking up your region into pieces that you recognize, which will be rectangular, triangular, and circular. And then those are things that you know formulas, or at least you believe them. And you're expected to use them to get the integral. Now I want to build on this example by asking you for the integral of f of x minus 4 over the same interval, minus 9 to 5. So it won't be a positive function anymore. That's okay. You just work it out using properties of integrals, which is what we've been doing. This is the integral of f minus the integral of 4. The first integral we just worked out. And the second one is the integral of a constant. That's something just from a minute ago. And you simplify this. 9 pi over 2 minus 23, that comes out around minus 8.86. So a little bit negative, and that is just your clue that you have more area underneath the x-axis than above the x-axis. So here's the graph. And if you look at it, you can believe that, yeah, probably the integral is negative. Now, this integral was easy to work out, but if you were to try to work out the three areas, there's an area below, area above, area below the x-axis, and then subtract, that would be horrendous. It would be actually very difficult. You would not want to do it that way. In fact, if you were to try to do it that way, the first thing you'd want to know is what the x-intercepts are. And even that is hard. So I would not encourage you to try to do it that way. But integrals really are easier to work with than areas anyway. So the first thing you should try is the properties for integrals, which is what I'm showing you here.